Hi, David Can here. We're in topic 5.4, and we're going to be talking about a few different syllabus points in this question. We have determining the direction of the magnetic field based on current direction, determining the direction of force on a current-carrying conductor in a magnetic field, and sketching and interpreting magnetic field patterns. So in this question, what we have is a card with two wires poking through the card perpendicularly. So there's a little right angle there, and there's a little right angle there. There's a current in each wire, and the current is downwards in each wire. We're looking down on the surface of the card. This is the same situation, but in a two-dimensional view. So we're looking down on the surface of the card. The question says, on diagram 1, draw the direction of the force on each wire. So the question implies that there's going to be a force on each wire, and indeed there will. Because the wires are full of charges which are moving, so we have moving charges, which will generate a magnetic field. The magnetic field generated by one wire will intersect the other, and so we'll have moving charges in a magnetic field that will experience a force. The other wire will generate a magnetic field which will affect the charges in the first wire. So both wires will have moving charges in magnetic fields created by the opposing wire, and so both wires will experience a force. Now we have to determine what direction that force will be. So the first step is to determine what the magnetic field generated by what we'll call wire 1 looks like. So that's wire 1, that's wire 2. We'll call that wire 1 here, and wire 2 there. For the magnetic field generated by a current-carrying wire, we have a second right-hand rule. Just like the other right-hand rule, we need to make sure we use our right hand. So if you're right-handed, put down your pen, put down your pencil. Make sure you use your right hand. The second right-hand rule looks like this. If you have a current-carrying wire, if you wrap your fingers around the wire, so your thumb points in the direction of current, and you wrap your fingers around the wire, the direction in which you wrap your fingers gives you the direction of the magnetic field. And the magnetic field winds up looking like concentric circles around the wire. Or maybe like concentric cylinders around the wire. So thumb goes in the direction of current, fingers wrap around. So let's see if we can apply this diagram to this situation. All right, current is going down. So what we want to do is we want to move our hand so that it's flipped all the way around. So if our hand is pointing down and we wrap our hands, we wrap our right hand around, we see that the magnetic field goes behind and in front. Behind and in front. The diagram is... let me try playing with the diagram. Give me a second. Nope, couldn't make the diagram any nicer. But what we see is if you point your right hand's thumb down and you wrap your fingers, you wrap them behind the wire and then in front of the wire. Behind the wire and then in front of the wire. Behind the wire and then in front of the wire. So you're always wrapping in this direction. Which means that in the region of wire 2, the magnetic field is in this direction. So in order to figure out the force on this wire, we'll use the second right-hand rule, or the original right-hand rule, the first. All right, we want to point our fingers, we want to point our thumb in the direction of current, so let's rotate and rotate. So our thumb is going down. But the magnetic field is out. So we want to point our hand outwards. Thumb is going down, fingers are coming towards you, which means that the force is to the left. Force is coming out of the palm of your hand. The force on the wire is to the left. So because the magnetic field in this region was pointing down across the page, the force is then to the left. So the force on that wire is to the left. What about the force on wire 1? Well, if you sat around on the other side of the table and looked at this card, it would be identical. So if we calculated everything in terms of the magnetic field on wire 2 and looked at wire 1, it would be the same situation in reverse. So the force on wire 1 has to be in the other direction. You can also think of this in terms of Newton's third law. Forces come in pairs which are equal and opposite. They have to be in opposite directions. So basically the forces are inwards. Part 2 says on diagram 2, draw the magnetic field pattern due to the currents in the wire. All right. Well, now we're looking straight down on the page. This X means that the current is going into the page. If it were a dot, the current would be coming out of the page. Since the current's going into the page, what you need to do is take your thumb, put it right on the page, and spin your right hand around. And it's going to spin around in that direction. You're going to get concentric circles in this clockwise direction. Do the same thing with wire 2 though, and you're also going to get concentric circles in a clockwise direction. Let's draw some bigger ones. Clockwise, 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 clockwise. Yikes. Getting ugly. But let's take note of 3 different regions. The region in the center, the region to the right, and the region to the left. In the center, the black lines are going down and the blue lines are going up. That means they oppose each other. Whereas on the left, both lines are going up, and on the right, both lines are going down. They add. So in the center, we're going to expect to find no magnetic field. The magnetic fields are canceling out. Whereas on the sides, we're going to find a clockwise up rotation and a clockwise down rotation on these 2 sides. So let's see if we can determine what that's going to look like. In the center, nothing, but on the sides, we're going to go around. But that means that we can't go through, because in the center there's nothing. So we're not going to go through, we're actually going to continue around. And then we can't loop through anymore, we're actually going to continue around. So in a clockwise direction, we'll go around, but we can't go through. We have to go down, but we can't go through. So we get this kind of peanut shape. Closer in, maybe we can go around, because we're not going to go into the dead center. So we'll go around in a clockwise direction, and we'll go around in a clockwise direction. And further out, we're going to get something even rounder. Again, in a clockwise direction. So we can see sort of the concentric circles of the one and the concentric circles of the other in sort of this region and this region, but in the middle they cancel out.